Okay, so today I'm going to cover up, try not to do too much of Sidense marketing here, but what I'm going to try and cover is why NVM, specifically OTP, is so necessary in every chip that's out there. And we are proliferating, so I'll talk a little bit about just a few slides on Sidense and what the current status is of how people are using our OTP, what the customers are looking for, and how we sort of help them out there. Oh, this one? No. Yeah, okay, so a little bit on Sidense. So we are a very well-established company out of Ottawa in Canada. We're more than 10 years old. We've been growing at a good rate of 45% a year, and we've got 65 employees and lots of support around the world. So what we call IoT, IoT is a buzzword, I think so as well, as most of you talked about, but we call it the smart connected universe. And when I say smart connected, it's sort of like IoT, but it sounds a little bit more or less cartoonish than IoT. So anyways, what we think is that the universe is going to be connected in a smart way. The automotive, wearables, mobile computing, medical, IoT is kind of a piece of that, and industrial. So that's our sort of way of looking at the entire universe that's going to be connected through the internet. So the way, again, we look at it is in sort of three sections. You've got the just to identify, D is for detect, S for smart, and C for connection. We call this is where IoT would sit. It's sort of the edge nodes, or sensing nodes. It's the sensing of the smart devices. It could have, it would definitely have, the detection part in it, but there could be some smarts in it. In some cases, no smarts, and definitely some way of communicating to the next level, which we call the hub nodes. And so that's where sort of the data gets integrated, maybe processed, and again communicating that back to the, let's say, to the cloud where there's big data and you do lots of fun stuff, which not too many people have figured out what to do with that big data, but it's coming. I believe it's coming. So in an example, this would be a smart watch or a sensor, or something that you're maybe a wearable or so on. And the hub node would be more like your smartphone and then the cloud. So that's sort of our representation of what we see as the smart connected universe. I think somebody else showed a similar chart earlier. It just shows that there's lots of growth in the IoT, and it's going to be billions in 2025. Nobody's going to argue with that one, right? So where does the non-volatile memory sit? It's a bit of a chart here. We've tried to capture what we're trying to say here, but if you look at the legend here, blue is for field programmability, red low power, operating temperature, and security. We said, you really want these three things, or features, or whatever you want to call it, as part of your NVM, when you choose your NVM. So if you look at the chart here, is on the y-axis is the cost of ownership, and here's the endurance, which is basically how many times you can write or program a single bit. So everybody's familiar with mass chrom. It's good as far as power and operating temperature is concerned, but really not good in security, and definitely does not have the field programmability that people would need in an NVM. And you can look at flash, floating gate, MTP, eFuse, and then of course this is our Sidense anti-fuse OTP. And it has all the four features. It's got very good field programmability. It sits very well with low power. We're doing a lot of work with IoT sensors. We're in sensors like crazy. Okay, I should stop pitching on that. But anyways, we do it all. It's one-time programmable and very cost efficient. So what does it look like? On the top right-hand side, it's the CMOS standard. This is our bit cell, standard bit cell. It's an anti-fuse technology. It actually makes a connection to the channel through the oxide by rupturing the oxide, the thin oxide. Here's a representation of the FinFET piece. I have a model in my bag. Don't ask me to explain that one yet. But the model I can explain well. It's 3D, I can see it, I can talk to it. But anyways, our solution is a very reliable OTP solution. It's non-reversible. It's standard CMOS. It's widespread industry adoption. We've done hundreds of millions of chips. And it's proven in silicon from 180 nanometers. That's where we start. We don't go above 180. So 180 nanometers down to 16 FinFET. We're doing FFC, FF+, and all that good stuff that TSMC is throwing at us. So where does the OTP sit in the smart connected universe? Here are just a couple of examples. It's in secure key and ID codes, configuration, code storage, secure code storage, analog and sensor printing. We've seen our OTP go on almost all of those in multiple devices. When we got started, we were actually doing security keys for HDMI because HDMI was big at that time, and there was I think there was a penalty of I don't know, $5 million or something if you lost your specific HDMI key. So everybody wanted to do it securely. People didn't want to use eFuse. They didn't want to use flash. So they said, what do we do? And they started using OTP. So we thought we'd be doing really well in that sort of segment. And over the last 10 years, we're just in almost anything that you can imagine. So it's a very good alternative to eFuse ROM and flash. There's multiple applications that I talked about. And then there's the smartphones. Here's a list of things that smartphone ICs use OTP in, for anywhere from configuration and boot ROM and so on. It's from the previous slide. We're in every one of those except for the baseband. Yeah, it's great because when somebody says, okay, so you're in the Apple phone, I go, yeah, we can't really talk about it. And he says, yeah, and you're in this chip, okay, we can't really talk about it. You're in this chip, we can't really talk. Well, there are almost a few chips on a given smartphone. And people have talked about automotive. I saw a really good slide from TSMC, so I'm really not gonna spend too much time on that one. But again, our OTP in a lot of automotive applications as well. Yeah, it's true. Customers are looking for 175C now. Started off at 150. We're getting ready for ISO 26262. A lot of stuff going on in there as well. This is obviously this is very exciting for Sidense. Okay, so what are the requirements for a smart connected universe as far as OTP is concerned? I think low cost, everybody knows about that. If we want to compare, let's say the different technologies, ROM from an area perspective, this is more an area. ROM were slightly larger than ROM, and one of our competitors slightly larger than us, using 2 transistors. Then there's floating gate MTP, and eFuse is massive compared to that, and as far as the area is concerned. On a reliability standpoint, again, we do a lot of qualification. Customers want to see this. This is really important. You can't really skip that step. It takes a lot of time, a lot of energy, a lot of money, but we do that. We do that for automotive quals as well, and we do that for every process node and every flavor that we offer our OTP in. So it's a huge, huge undertaking, and as well as characterization. And the characterization, again, is important because we want to make sure that our customers are using our OTP in the right way. So first time right, given the programming algorithms or programming voltages, they put it in, program it, and the story is good. Low power operation, obviously in the last, I'd say 5 years, this has become a big focus. We are going into ULP processes. We focus on low voltage reads, focusing on below 1 volt. It's a challenge, but we're doing a good job, and you'll see a lot of products with our OTP and low power operation. Now this is something that I would like to spend more time on it. We started off like that. I mean, the HDMI keys were supposed to be secure. You know, you had to, as I mentioned, pay a lot of money if it got hacked. We started off like that, and we spent some time on it, and we're finding that our OTP has a lot of good features actually inherent to it, and as well as the circuitry that we put around it. So there are 3 pieces that you want to focus on as far as security is concerned. It's the physical attacks, it's tamper resistance, and the side channel attacks. And we're pretty good at all 3 pieces. So for example, we don't store any charge. So as far as physical attacks, it's we have actually delayered it multiple times, and it's very, very difficult to see even 1 bit being programmed. So if you've got a few kilobits, you better have millions of dollars to actually figure out what it's written, and maybe you'll have a good chance. What else can I talk about? So from a tamper resistance perspective, we put all sorts of logic around our OTP, so the macro that we sell. So we've got the bit cell, we've got the programming macro, we've got the sensing scheme, and all the digital logic around it that makes up the entire OTP macro. And then there's flexibility built into it. The way we really like the way it's architected. This has been around for, again, 10 years. If you look at, let's say, a 64 kilobit block of OTP, which is, let's say, configured 4K by 16, really you can use it in multiple ways without even configuring it that way. So if I deliver 64K bits in 4K by 16, and you decide, okay, you know what, I need to use it in 8 kilobits redundant mode. So we've got redundant cells built in. It's for higher reliability. Automotive guys like the redundancy built into it. You can just basically pick a sector, and the way we've configured it, you can use 2 bits per cell as opposed to 1 as a single bit. If you want to use it as an eMTP, which is emulated multi-time programmable, which we see that a lot of our customers are trying to maybe use it 10 times, 20 times, 30 times, even sometimes 50 times, we give them a bigger bank, and we say, okay, for example, if you want to use it 16 times, we'll give you 512 bits configured 16 times, and then you can just find the address and write accordingly and read accordingly. That's working out really well. I'd say 25% of our customers use it as an eMTP mode. They find that the floating gate is too big, too large to do a few kilobits. They also use it in single-ended mode. And if you really have your code fixed, you can change one mask, which is a diffusion mask, and turn it into a mask ROM. So if you buy a 1 megabit OTP from us, tester time is going to be fairly crucial. If you want to write the same thing over and over again, you can take the same chip, you swap out a mask, your code is fixed, and you can burn that code into mask ROM, and your tester time just goes down. So it's a built-in feature. Again, you don't even have to tell us if you're going to use it as a mask ROM. It's good that you do, so we can guide you through the process, but So anyways, that's where the flexibility is built in. And I think this is really important. Then we support a lot of the specialty processes. Right now, BCD is a very hot market, 180, 130 BCD. The HV and CIS processes, I think some of the foundry partners spoke about that earlier. And that's going into display drivers, image sensing, power switching. These are all very good alternatives. Customers are using eFuses, are switching to us, maybe other NVM technologies. So we've covered over 11 nodes in specialty processes and across 5 foundries. We work with IDM very well as well. So this is an example of 130 BCD. Again, I'm not going to spend too much time on it, but it's good to have the 150. We've got power down mode. This is a PMIC, PMIC and sensor chip. So I guess it just shows how our OTP is used as a boot code and boots up the sensor device and so on. So actually the OTP is used in 3 different ways. Same OTP for boot code, for device configuration and analog trimming, as well as for device ID and security. So that's a good example of multiple use with one OTP. So you're not using eFuses or flash or other technologies to do different things. This is another plugin. I guess we've covered all sorts of feature sizes, and these are our different product lines, and they're to accommodate different voltages, different requirements. If a customer wants to use it as a programmable solution and then a mask-ROM, it sits at SiPROM. If you're going to use it as a fuse replacement, it sits as SiFuse. So we have made sure that we've got the right control circuitry, but using the same bit cell. So the bit cell is always exactly the same. So here's one of the smart IoT things. I don't know if you guys can read that, but you can see the picture, right? It says, "Bad news, the scale is threatening to cut off our access to the fridge." And thought the marketing guys liked that, so we put it in there. And that's about it. Oh no, sorry, the summary slide. So just to summarize, so again, we called all the stuff that's happening with IoT and so on, we call it the smart connected universe. We think that if you saw the joke before, I mean, it's kind of senseless to do something like that unless you're suffering from being overweight or something, but she didn't look like she was overweight. Anyways, so it is an anti-fuse based technology, which is one-time programmable. It meets all the smart connected universe requirements very, very well. It's cost effective and is a very good replacement for the current NVM technologies that are on the market. Thank you very much.